Welcome to Physical Science, Module 14. We'll begin with learning some items about waves and sound. The vocabulary we'll be covering in this video is electromagnetic waves, crests, troughs, wavelengths, amplitude, frequency, transverse waves, oscillation, longitudinal waves, compressions, rarefactions, and hertz. There are many common types of waves. We usually think about water waves when we're thinking about waves, but actually some of the most prevalent waves are electromagnetic waves, which are light. Air waves are also very common, and waves found in water are also there, but they're not the most prevalent. Let's talk about transverse waves. The picture here from your text shows a transverse wave. This is if you were looking at a side view of the wave. And we have crests, which is the highest point on the wave. Then we have troughs, which is the lowest point on the wave. And then we actually have wavelengths, and wavelengths are the distance between the crests or between the troughs. So this is the actual length between the high points or the low points. We have amplitude, which is the height of the wave, and what they're showing here with this line would be an example of what you would see with water. This line would be the horizon line, or the flat part of the water that you see at the beach. And this would be the wave above the water. This would be the wave below the water. And we have frequency, how many waves hit a certain point every second. If the wave crests are far apart, few waves will contact you in a second, so the frequency is small. So if you're standing out in the ocean and the wave crests are far apart, you can stand there for quite a while between the time one wave hits you and then another wave comes. So if the crests are far apart, frequency is small. If the crests are close together, several can hit you in a second, and the frequency is large. So the opportunity is large that you will be hit more often with waves, and that's when you start to get a little panicky and want to get out of the water. Wavelength and frequency happen to be inversely proportional to each other. So if the crests are close together, frequency goes up. If the crests are far apart, frequency goes down. Frequency and wavelength can be related to one another through the speed of the wave. And we actually have a formula you need to write down here. And it is F, which means frequency, equals V. And V in this instance is just speed. It's not velocity like we've learned before. For it to be velocity, it would have to have a direction, and this is just the speed that the wave passes a given point. And then this funny little character below here is actually called lambda in Greek, and that indicates wavelength. Speed is measured in meters per second, while wavelength or distance is measured in meters. If you divide meters per second by meters, you will have 1 second left. So let me say that again. If you divide meters per second by meters, so that would mean in an equation you would be crossing out both m's, you would just have 1 second left. This 1 second is the unit for frequency, and in science they call this unit for frequency a hertz. And the reason they call it a hertz is this is a gentleman who actually discovered sound waves. So a transverse wave is a wave of the direction of propagation that is perpendicular to its direction of oscillation. In other words, a wave with a horizontal direction that is perpendicular and moves up and down. Think of a rope held by two people that's flicked up and down at one end. A wave moving towards the other person would travel from that end of the rope to the other end of the rope, and that's called propagation. So two people are holding a rope. They're holding it taut, and then one person flicks that rope up and down at one end. The wave actually travels towards the person not moving the rope. The wave would also move up and down because the person jiggling the rope is moving it up and down. This is called oscillation. Now, longitudinal waves are different from that, and when thinking of longitudinal waves, you need to think of a slinky. If you lay a slinky on the ground, portions of the slinky are compressed. They stick together while other portions are pulled apart. The compressed sections are called compressions, and you should think of them like the crests of the other waves that we learned about. So this will be the high point. Instead of being high, it'll just be where they're lumped together. And the pulled apart sections are called rarefactions. These would be similar to the troughs of the other waves. The troughs were the lower part of the wave, and in this one it'll be the stretched out part of the wave. As time progresses, the compressions move from left to right, and that's the actual direction of oscillation. Both the direction of propagation and oscillation are horizontal. The difference between the two types of waves is the first wave, the transverse waves, is actually perpendicular, and the longitudinal wave is parallel. So let's take a look at an example. Example 14.1 from your text says, what is the frequency of a wave that travels at a speed of 3 meters per second and has a wavelength of 0.05 meters? So from our formula, we know that the frequency equals the speed divided by the wavelength. So the speed is 3 meters per second, and it's being divided by the wavelength of 0.5 meters. We can cross-cancel the meters out, and what we have left is 3 divided by 0.5, which is 6, and we have 1 over seconds left. That 6 over 1 seconds is equal to 6 hertz, which is also shortened to Hz. So, if you have any questions, be sure to contact me. We'll be working more examples later on, and we'll move on to the next video.